All right, we are now ready to move on to section 2.3. The limit laws. The limit laws. Okay. Excuse me. So what we have done so far is we learned how to find what the limit is by using a table or a graph, right? The graph isn't too bad, but what happens if the graph is hard to sketch out, right? In that case, it's not really the best plan to try to do it from the graph, right? And then the table, although it worked, as y'all could see, took a really long time, right? I would have to sit there and type everything out, write everything out. It took a very long time whenever I feel like we shouldn't have to spend so long writing everything out, right? So what I want to learn here in section 2.3 is how to actually find what it is using the equation itself, okay? Which is going to be very helpful. So we have, to start with that, we have two very basic limit laws. Real basic, okay? The first one is that the limit as x approaches a of x. So if it's just an x, okay? If it is just an x, the answer is a. Let's think about y, okay? As x is approaching a, I'm wanting to know what x gets close to, right? Because that's what I'm saying right here. But as the notation states, x is approaching a. So it makes sense that x is approaching a because that's what we wrote down here, right? So if it's just an x, it's whatever I get close to, okay? So if I was doing the limit as x approaches 2 of x, well, I said here, x is approaching 2, so x is approaching 2. If I was saying limit as x approaches negative 3 of x, then obviously it's negative 3, because we wrote down right here, that's what x is getting close to. So that's my first real basic law there. The second one, limit as x approaches a of a constant. So if I just have a constant right here. So notice I'm saying x is approaching a, right? So I'm saying as x gets really close to a. Well, since this is a constant, it's always the same thing. So it doesn't really matter what x is getting close to because it's always a constant. So if it's a constant, the answer is just the constant. So what I mean by that is the limit as x approaches 3 of 10. Well, 10 is always 10, no matter what x is. So this is 10. Again, because 10 is always 10. Same thing if I was doing the limit as x approaches 92, I don't know, of 8. Well, 8 is always 8, so it doesn't matter what x gets close to, right? It's always 8. So the answer would be 8. So the good thing about having these two now is I can use these two easy laws here to do a lot of really neat stuff, okay? Before I can do that really neat stuff, we have to write down all the other laws that I'm going to use, okay? So let's write down all the other ones. So these are the limit laws that are going to help us out by finding them using the equation. The first one is that the limit as x approaches a thing, I'll just say a, of f of x, plus the limit as x approaches that same a of another thing, g of x. I can actually do this by making it one thing. So that's the limit as x approaches a of f of x plus g of x. I can combine those into one term, into one thing. On the same note, if I see something like this, I could actually split it up into two terms because I could do each one of these as opposed to as opposed to at the same time, right? Same thing if I'm subtracting, I can just subtract them. So if I have limit as x approaches a of f of x minus the limit as x approaches a of g of x, I can subtract them together. So the limit as x approaches a of f of x minus g of x. So that's helpful. If I'm multiplying by a constant, so if I'm saying the limit as x approaches a of a constant times f of x, since this constant does not have an x, I can actually just bring it out front and make it c times the limit as x approaches a of f of x. This is a trick we are going to use a lot throughout this whole class, Calc 1, and you will see it a lot in Calc 2. Okay, if there's just a constant, I can just bring it out to the front. Okay, another cool limit law is if I am multiplying, so the limit as x approaches a of f of x times the limit as x approaches a of g of x. Again, just like I have done, I can just multiply the functions. So f of x times g of x. That's really helpful. Dividing works the same way. So if I have the limit as x approaches a of f of x, let me rewrite that. I wrote that a horrible way. Limit as x approaches a of f of x divided by the limit as x approaches a of g of x. I can make this one term by just doing the limit as x approaches a of f of x divided by g of x. Like that. We have more laws, but I ran out of room, so I'm erasing another board. Remember, y'all can like hit pause if you need to write this down or whatever you're trying to do. We have two more. Both of these are extremely helpful. If I have the limit as x approaches a of a function raised to the n. So if I have a thing raised to a power, what's really cool is I can just take the limit of f of x, and after I do that, just raise that to the n. So it's the same thing if I raised it to the n first, or if I did that afterwards, that doesn't matter. They're the same thing. On that same note, if I'm taking the limit as x approaches a of a root, so I'll just say the nth root, that could be the square root, that could be all kinds of roots, of f of x, what I can actually do is take the limit first of f of x, and then just take the nth root of all of that. So these are all rules that are going to help us out. Let's look at some examples of how. Example. Let's find the limit as x approaches negative 3 of 4x plus 2. So how we have done these beforehand is that I would have had to write out a bunch of points to the left and then a bunch of points to the right and plug them in and seeing what it gets close to, right? Well, now with these laws, I don't have to do that. Okay, I can separate this as much as I can to figure out what it is. So the limit as x approaches negative 3 of 4x plus 2, since I'm adding these up, I can split it into two terms and do plus. So I could do the limit as x approaches negative 3 of 4x plus the limit as x approaches negative 3 of 2. I can break that up like that. Well, now I can see right inside of here I have 4 times an x, right? So since I have a constant right here, like we said, I could bring my constant out to the front. So that's like saying 4 times the limit as x approaches negative 3 of x plus the limit as x approaches negative 3 of 2. Now let's think about why I might want to do this, right? Because now it looks like there's more terms right here, and so it would take more work, right? But look, I know how to find both of these here, right? The limit as x approaches negative 3 of x, we learned that's just negative 3, right? Because whenever I have an x right here, it's just whatever I'm getting close to. So I could do that. We also know how to find this of 2, right? As x gets closer to negative 3 of 2, since that's a constant, it's just 2. So now I can multiply everything out. 4 times negative 3 is negative 12. So I'm doing negative 12 plus 2, which is negative 10. So the answer is negative 10. So what I'm trying to do here is to separate this as much as I can so that I can actually find what they are without having to plot a bunch of points. That's what I want to do. Okay. So I separated this. Since I'm having plus right here, I can make it this plus that. Bring my 4 out to the front. I know what this is and I know what that is, so I'll just plug them in and I'm good. This is a lot less work than how we learned it in section 2.2. So let's look at another example. Let's do the limit as x approaches 2 of 2x squared minus 3x plus 1 over x cubed plus 4. So I can do the same thing here. This is a lot of terms, but I can break that up using my laws, right? So since I am dividing them, I know I can just do each part. So the limit as x approaches 2 of 2x squared minus 3x plus 1 over the limit as x approaches 2 of x cubed plus 4, right? I can just do each part there. Well, now on each the top and the bottom here, I can see I can use my laws even more, right? I can use it even more. So I can write this with my first term being 2x squared. My 2 I can bring out front, so that's 2 times the limit as x approaches 2. It was x squared, but remember we had the rule where if I have a power, I can bring it outside, right? So that's the limit as x approaches 2 of x, and I'm going to square that because of the squared. Then I'm going to subtract the number out front of this one's 3. So 3 times the limit as x approaches 2 of x. Then I just have a 1, so that's the limit as x approaches 2 of 1. That's everything on top. Do the same thing down here. This is just an x to the third, so I can do the limit as x approaches 2. Yeah, as x approaches 2 of x raised to the third. Move on over here. That's the limit as x approaches 2 of 4. Again, this looks like a lot of terms. It looks like a huge mess, right? But this is actually less work than this was because I know what each of these are, right? I can do each of those. So this becomes the limit as x approaches 2 of x is 2. So that's 2 times 2 squared. The limit as x approaches 2 of x, we already said was 2. So that's minus 3 times 2. The limit as x approaches 2 of 1, because that's a constant, it just stays 1. The limit as x approaches 2 of x is 2, so that's 2 to the third, plus the limit as x approaches 2 of 4. 4 is a constant, so it's just 4. So I just have to work that out. So 2 squared is 4, so that's 2 times 4. Minus 3 times 2 is minus 6. 2 to the third is 8, so that's 8 plus 4. 2 times 4 is 8, so that becomes 8 minus 6 plus 1 over 8 plus 4. 8 minus 6 is 2, 2 plus 1 is 3, over 8 plus 4 is 12, and reduce that to 1/4. So, like I said, the very cool thing about these is I can break it down into something that's not very hard, right? Because I know each of these. Now let's see if you noticed something about these last two that I did, okay? So using the laws, this first one we did right here, I was able to like bring out a 4 and everything. The limit as x approaches the negative 3 of the x, and then I had this over here too, right? And I ended up with a negative 10. Well, if you look at this, once I broke it down to this step, this looks exactly like what I had up here, except I plugged in a negative 3 for x, right? But it looks the same. Well, let's think about what's special about that. -3 is what x is getting close to. So basically what I did was plugged in -3 in here for x, right? Plug that in there for x, and I get to this step right here. Let's see if the same was true for this one I just did. Notice what I broke it down to was this, which is exactly what I started with, except I plugged in a 2 for x, right? Because I have 2 times 2 squared, minus 3 times 2 plus 1, and then 2 to the third plus 4. I just plugged in this 2 in here for x. So that fact actually helps us out even more, because now I don't even have to write all of this out. I know I can just plug in, quote unquote, plug in the number for 2. Okay. But a point I want to make super clear is that only works if the function is defined at that point. If not, then if I plugged it in, it doesn't work, right? And we will see examples of that. So let's use that idea and do this example. Let's do the limit as x approaches -2 of 3x to the third minus 2x plus 8. Let's do that. So the first thing I want to see is this defined at the point I want. Well, since there are no domain restrictions here, I can see I can plug in any value of x that I want. So since I can plug this in, let's just do that. Just plug it in. So 3 times -2 cubed minus 2 times -2 plus 8. -2 cubed is -8, so that's 3 times -8. -2 times the -2 is +4 plus 8. 3 times -8 is -24. 4 plus 8 is 12, so you get -12. So it's simply equal to -12. But again, the only reason that worked was because the -2 is within the domain of that guy. Okay, I can plug it in, so go ahead and do that. Okay, let's look at another one and see if it will work for this one too. Limit as x approaches 3 of 2x squared minus 3x plus 1 over 5x plus 4. So since I have a denominator, there is a domain restriction here, right? So I first need to see if it is even possible for me to plug that in, right? Well, I can see I will be good here because the only thing x can't be, I can find that by doing 5x plus 4 can't be equal to 0. So 5x can't be equal to -4. So x can't be equal to -4 over 5, right? So that's the only thing x can't be, so I am good by just plugging in 3. So just plug in 3. 2 times 3 squared minus 3 times 3 plus 1 over 5 times 3 plus 4. 3 squared is 9, times 2 is 18, -3 times 3 is -9, plus 1 over 5 times 3 is 15, so 15 plus 4. 18 minus 9 is 9, plus 1 is 10. 15 plus 4 is 19. So 10 over 19. Again, I can do this one just by plugging it in because 3 is within the domain there. So there's no problems. Let's do some more examples. Another way to think about this. So remember, the idea is I want to know what happens to the graph of this as x gets close to 3, right? Well, if 3 is a point, then this graph is going to get close to that point, right? Because there is actually a point there. So obviously I'm going to get close to that point. Okay, so that's why I can just plug in 3 there. Let's do another example. This one's really good. I like this example. let's do the limit as x approaches 1 of x squared minus 1 over x minus 1. Okay, let's think about this one. If I were to try to plug in a 1 here, notice the denominator would be equal to 0, which I cannot have. So since this is not in the domain, it doesn't work as cleanly as just plugging in a 1. Okay? So what I've got to do is look at this and say, okay, is there a way I can rewrite it? Is there anything I can do here? If I look at the top part, I see x squared minus 1 can be factored out, right? X squared minus 1 can be factored to be x minus 1 times x plus 1. So let's do that and see if it helps us. So that's going to be equal to the limit as x approaches 1. Remember we said we can write this as x minus 1, x plus 1. Now let's look at that and see why that might have been a helpful step. If you notice, x minus 1 appears on top and down here, right? So I can actually cancel them out. So that's going to be equal to the limit as x approaches 1. All I have left is x plus 1. Now that I have it down to this, I can just plug in a 1, right? Because 1 is within the domain of this, and so I can just plug in a 1. So that's going to be 1 plus 1, which is 2. So my point for this one is that if it initially looks like it cannot be done, let's see if I can rewrite any part of this to make it into a form I can do. Okay? In this case, that was factoring out the numerator. Let's look at another example of that. Let's do the limit as x approaches 3 of x squared plus 4x plus 3 over x squared minus 9. Alright, so the same thing here. If I were to try to plug in a 3 in the denominator, I would have 3 squared minus 9, which would be 9 minus 9, which I can't have, right? So I can't just plug this one in, so I'm going to have to try to rewrite this as best as I can. So let's see if any of these can be factored out. Well, on top I have x squared plus 4x plus 3. So I can factor this by finding the factors of 3, whose sum is equal to 4. So I can tell that factor is going to be x plus 1 times x plus 3 over. And then now let's factor x squared minus 9, just like I did right up here. Since this is x squared minus 3 squared, I can factor this to be x minus 3 times x plus 3. So in looking at that, I can now see this is supposed to be the limit as x goes to negative 3. So sorry. I was like, that's super weird. Sorry, negative 3. My apologies. And I forgot to write the limit over here. Negative 3. Make sure you change that to negative 3. So sorry about that. Okay, continuing on. Now I can look right here and see, okay, how did that help me out? Well, I can see there's an x plus 3 right here and an x plus 3 right there. So I can cancel those out, which gets me to the limit as x approaches negative 3 of x plus 1 over x minus 3. The reason that's helpful is because now I can just plug this in for x. So that's going to be negative 3 plus 1 over negative 3 minus 3. Negative 3 plus 1 is negative 2. Negative 3 minus 3 is negative 6, which reduces down to 1/3. So the limit is equal to 1/3. Let's do some more examples. Let's do the limit as x approaches 3, and that time it really is 3. X approaches 3 of x squared minus 3x over 2x squared minus 5x minus 3. So same thing here. If I were to try to plug in a 3 into here, the bottom would be, so let's see, 3 squared is 9, times 2 is 18, 5 times 3 is 15, so minus 15 minus 3, which is 0, which I can't have, right? So it doesn't work like that. Let's try to factor this out. On top, I see both of those have an x, so let's factor out an x. So that's x times x minus 3. On the bottom right here, I would need to factor that out. If you were to factor this, there's a lot of ways to. I'm going to show you one way, but there's a lot of ways to factor this out. How I do this is I first say, okay, let's do a times c. I'll do it down here. A times c, which would be 2 times negative 3, which gives you negative 6. So I need to find the factors of negative 6, whose sum is equal to negative 5. So I can see that's positive 1 and negative 6. So I'm going to use this to split the middle term into 2 terms. So that's going to be 2x squared plus 1x minus 6x minus 3. Both of my first 2 terms have an x, so factor out an x. So we're left with 2x plus 1. Both of those have a factor of negative 3, so factor out negative 3. And again, I'm left with 2x plus 1, which means my factored form is both of those have 2x plus 1, and I'm left with x from my first term and minus 3 from that term. So the denominator factored is 2x plus 1 times x minus 3. That is a pre-cal skill, so if you don't understand how to do that, let me know and I will be happy to help you out, okay? There's a lot of ways to get that. I just like doing it like this, but that's just me. Once again, I forgot to write the limit. Make sure you are writing the limit. That's how I make it correct. Make sure you write that. So sorry. So the reason this is a good thing is because I can just do x minus 3 canceled out on both of them. So that's going to make it the limit as x approaches 3 of x over 2x plus 1. So now I can plug in a 3. So that's going to be 3 over 2 times 3 plus 1. So that's 3 over 2 times 3 is 6, so 6 plus 1, which gives you 3 over 7. There we go. Let's continue on. Let's do a little bit more complicated examples. These still aren't bad. Still pretty good, but they just require a little bit more thought. Example. Let's do the limit as x approaches negative 1 of the square root of x plus 2 minus 1 over x plus 1. All right, so again, just like on the last ones, if I tried to plug this in, then in the denominator, I would have negative 1 plus 1, which is no good, right? I can't have that. So I've got to try to rewrite this some way, okay? Normally, I would try to factor something out, right? But if I look at this, nothing can really be factored out. So I'm going to try to do something else, okay? Anytime you see a square root, remember I can get rid of this square root by multiplying by the conjugate, right? So since I have a square root up here, one way I can rewrite all of this is to multiply it by the conjugate of the top. So what that means is multiply it by square root of x plus 2 plus 1. If I do it on the top, I've got to do it on the bottom as well. So square root of x plus 2 plus 1. Now let's see why that's a good thing, okay? If I did the square root of x plus 2 minus 1 times the square root of x plus 2 plus 1, what happens is I do the square root of x plus 2 times the square root of x plus 2. Since that's like doing a square root squared, I just end up with x plus 2. Square root of x plus 2 times 1 is plus the square root of x plus 2. Negative 1 times the square root of x plus 2 is minus the square root of x plus 2. Negative 1 times positive 1 is negative 1. So the reason this is helpful is because now look what happens right here. That's the square root of x plus 2 minus the square root of x plus 2. They cancel out. So I'm just left with x plus 2 minus 1. 2 minus 1 is 1. So that ends up just being x plus 1. So what this ends up being is the limit as x approaches negative 1 of, we just said on top, that becomes x plus 1. And the denominator is x plus 1 times the square root of x plus 2 plus 1. Now the reason that's so helpful for us is because now look, I have x plus 1 on top, x plus 1 down here, so they cancel out. So now I'm left with the limit as x approaches negative 1 of, everything is gone from the top, so we just put a 1 there, over, on the bottom I have square root of x plus 2 plus 1. And now I can plug in a negative 1 to this. So that's going to become 1 over the square root of negative 1 plus 2 plus 1. Negative 1 plus 2 is just 1, so that's square root of 1 plus 1. Square root of 1 is 1, so 1 over 1 plus 1. And 1 plus 1 is 2. So 1 over 2. So my point for this one is that a good trick to get rid of a square root, if I have one there, is to multiply by the conjugate. Okay. Let's do some more examples of that one. Something else, actually, yeah, sure. I'll write this down. So notice here what happened was what I get in this step is just the square root squared, which would be x plus 2, minus my second term squared. So 1 squared is just 1. So what I get is x plus 2 from right here, minus 1. That's the whole trick about that you probably learned in pre-cal or some point in time. A minus b times a plus b is equal to just a squared minus b squared, which is exactly what happened here, right? I had something minus a thing, and there was the same two terms over here, except my sign changed. So I can just square this, which gave me x plus 2, minus, and then square the 1. So 1. So that's actually why we do this, is so that I can use that trick and just get rid of those square roots. Okay, let's do another example like that one. Limit as x approaches 5 of the square root of x minus 1 minus 2 over x minus 5. So again, the same thing here. If I were to try to plug in a 5 right there, I would get 0 down here, which I can't have. So I'm going to have to try to rewrite this. Since I see a square root, I can do the same trick as what I did on the last one, right? I can multiply it by the conjugate of that. So square root of x minus 1 plus 2. If I do it on the top, I've got to do it on the bottom as well. So just like we saw on the last one, what happens then is it becomes the square root squared, which would just be x minus 1, minus this 2 squared. 2 squared is 4. All over x minus 5 times the square root of x minus 1 plus 2. On top, that becomes negative 1 minus 4 is negative 5, so x minus 5 times x minus 5 times the square root of x minus 1 plus 2. These cancel out. And so now I end up with just the limit as x approaches 5 of 1 over square root of x minus 1 plus 2. And now I can just plug in the 5. So plugging in, that's a 5. So if I plug in a 5, that's 1 over square root of 5 minus 1 plus 2. 5 minus 1 is 4, so that's 1 over square root of 4 plus 2. Square root of 4 is 2, so that's 1 over 2 plus 2. 2 plus 2 is 4, so that's 1 over 4. So that's how I would handle these if I see a square root there. We have some more examples we're going to do. Lots of examples, which is good. That means y'all are going to see a lot of them to help you out. This one's good as well. This one's going to be the limit as x approaches 1 of 1 over x plus 1 minus 1 over 2 all over x minus 1. So for this one, again, if I were to try to plug in a 1 right here, it wouldn't work. And so I've got to try to change this in some way. I can see straight up that this is going to be a pain in the butt because I have a fraction within a fraction, right? Just looking at that is scary. It's really not too bad, though, because what I can do is get rid of these extra denominators by multiplying by the least common denominator, right? So how I do that, I see on top right here, I have a denominator of x plus 1 and a denominator of 2. I want to get rid of those. So how I'm going to do that is multiply by 2 to get rid of the 2, and by x plus 1 to get rid of the x plus 1. But remember, if I do that on top, I've got to do that on the bottom too. And the point of that, again, is just to get rid of these denominators here. So multiply by 2, which will get rid of the 2, and then by the x plus 1, which will get rid of the x plus 1. So let's work this out. Limit as x approaches 1. 1 over x plus 1 times 2 times x plus 1. The x plus 1s will cancel out. So I'm left with just 1 times 2, which is 2, minus 1/2 times 2 times x plus 1. 1/2 times 2 is just 1. So I'm subtracting x plus 1 because the 2's cancel out. That's all going to be over. I like having the constant out at the front, so I'm going to do 2 times x minus 1 times x plus 1. Let's see if I can keep rewriting this until something works out. So up here I have 2 minus x minus 1 over 2 times x minus 1 x plus 1. 2 minus 1 is 1, and so that's the limit as x approaches 1 of negative x plus 1 over 2 times x minus 1 times x plus 1. Now, as it stands right now, there's nothing I can do here. But if you notice right here, this looks a little bit like the factor I have right here, except my signs have changed, right? I have negative x, whereas down here I have positive x. I have positive 1 right here, whereas down here I have the minus 1. So these are the same except for the signs, right? So what I can do is factor out a negative, which will make it x minus 1. And the reason I would want to do that is because now they do match up, so I can cancel those out. So that's the limit as x approaches 1 of negative 1 over 2 times x plus 1. And now I can plug in the 1. So plug in the 1, negative 1 over 2 times 1 plus 1, negative 1 over 2 times 2, 2 times 2 is 4, so that's negative 1/4. So again, how I can handle these is multiply by the 2 to get rid of the 2, and multiply by the x plus 1 to get rid of the x plus 1. And then simplify it out, which would give you negative 1/4. Let's do another example of that. I have a bunch of these, so we're going to do a lot of them so that you can see a bunch of different examples of this stuff. Let's do the limit as x approaches negative 3 of 1 over x plus 2 plus 1 over x plus 3. So again, just like I have done, I'm going to see first, can I plug that in for x, and I look right there and I can't, because if I did, I would get negative 3 plus 3, which is 0, which I can't do. So I'm going to have to rewrite this in some way. Just like in the last one, I can see here I have a denominator of x plus 2, so it would be helpful if I could get rid of that. So how I do that is multiply by the only denominator I have is x plus 2, so multiply it by x plus 2. If I do it on the top, I've got to do it on the bottom too. So that becomes the limit as x approaches negative 3. On this first term right here, x plus 2 cancels out, so I'm left with just a 1. And then I do 1 times x plus 2. 1 times x plus 2 is x plus 2. Then let's leave this as x plus 3 times x plus 2. Simplify the numerator, and we see that's the limit as x approaches negative 3 of 1 plus 2 is 3. So x plus 3 over x plus 3 times x plus 2. So I can cancel out x plus 3, which would give me the limit as x approaches negative 3 of 1 over x plus 2. And I can now just plug it in. So that's 1 over negative 3 plus 2. Negative 3 plus 2 is negative 1, so that's 1 over negative 1, which is negative 1. Negative 1. All right, I have some more different types of examples we're going to work through. Again, I just want to make sure y'all see every possible example you might see so that you're not doing this stuff blind. This one's also a good one. All of these are. These are very fun. I like these. I'm very happy whenever I do these because it looks really hard, and so like you feel really smart whenever you have it done. When really, this isn't really anything new, and so that's very cool. It looks hard, but it's not too hard, and so you feel really smart whenever you are done. Anyway, sorry, enough about my nerdiness. Let's do the limit as x approaches 0 of 1 over x plus 5 over x times x minus 5. All right, so for this one, I don't really have a fraction within one like I did over here. So doing this trick really wouldn't help me here because I'm not dividing by more stuff, right? So instead, what I want to do is try to add these up to make it one term and see what that does, okay? In order to add these, I need a common denominator, right? Well, I see both of them have the x, so that's a good start. But this one also has an x minus 5. So I need it over there too. So I need to multiply this by x minus 5. If I do it on the denominator, I'm going to do it on top as well. So this becomes the limit as x approaches 0 of 1 times x minus 5 is just x minus 5 over x times x minus 5. I did not change that one, so it's going to just stay. Now that the denominators are the same, I can just add up what's on top, right? So I have x minus 5 plus 5. The 5's cancel out. So that's just the limit as x goes to 0 of x over x times x minus 5. Again, I got that by doing x minus 5 plus 5. Well, what's helpful right here is now they have an x and an x, so I can just cancel those out, which gives me the limit as x goes to 0 of 1 over x minus 5, which means now I can just plug it in. So plug in as 0 for x. That's 1 over 0 minus 5. 0 minus 5 is negative 5, so negative 1/5. Again, what I would do is just make this one term, but in order to do that, I need a common denominator. So that's what I do, is get a common denominator. Another example. Told y'all, I got a lot of these. I was ready to go. Another example. Let's do the limit as x approaches 3 of 1 over x minus 3 minus 4 over x squared minus 2x minus 3. Okay, so what's going to be helpful with this one to find a common denominator? would be if I factored this out. So let's do that first, okay? I would need the factors of -3, whose sum is equal to -2. Well, I can see that would be -3 and +1. So let's go ahead and factor that. X minus 3 times x plus 1. So now I need to see what I can do to get a common denominator, right? Well, I see both of them have an x minus 3, so I'm good with that one. But this one also has an x plus 1, so I need to multiply it by x plus 1 to make sure that they match. So this means what I get is the limit as x approaches 3. 1 times x plus 1 is x plus 1 over x minus 3 times x plus 1. I did not change this one, so I'm just going to write it. So now that the denominators are the same thing, I can just add up what's on top. So x plus 1 minus 4. 1 minus 4 is -3. So that's the limit as x approaches 3 of x minus 3 over x minus 3 times x plus 1. And what's helpful about that is now x minus 3's cancel out. So I just have the limit as x approaches 3 of 1 over, all I have left is x plus 1. So now I can plug in a 3 for x. So that's going to be 1 over 3 plus 1, and 3 plus 1 is 4. So 1 over 4 for that one. Again, a trick about all of these is just rewrite it until it is a form I can do. So we're just rewriting stuff as best as we can. All right, I have a few more examples I want to do. Just a few. Let's look at the limit as x approaches 3 from the left of the square root of x minus 3. As x approaches 3 from the left of the square root of x minus 3. So let's think about this. Your first thought would probably be, okay, I can just plug in a 3, right? So I can just plug in a 3, easy peasy, no big deal. 3 minus 3 is square root of 0, so 0, and I'm done. But be mindful about what this means, okay? This means as I approach 3 from the left side, right? Well, let's think about what happens on the left side of 3, right? That would be like 2.9 or 2.99 or something like that kind of stuff, right, on the left side. If I plugged in a 2.9 into here, that would be the square root of 2.9 minus 3, so the square root of -0.1. But then think about that. Can I take the square root of -0.1? And I would say no. Because the inside of the square root always has to be positive, right? That's what we said. The inside of a square root always has to be positive. Since on the left side of 3 it's not, everything to the left side of 3 would be undefined. So because of that, this limit does not exist. Again, because on the left side of 3, the function is undefined. Whereas, if I did it on the right-hand side, limit as x approaches 3 from the right-hand side of x minus 3, this one would work because everything to the right side of 3 does work, right? I can do that. I can plug in 3.1 and 3.01 and all of that stuff. So this would be fine to do the whole square root of 3 minus 3, square root of 0. So boom. That's fine because everything to the right side is good, right? Whereas over here, everything on the left side, I cannot plug it in. So on that note, I try to think about what I can say about the limit as x approaches 3 of square root of x minus 3. And if we think about that, we would say that does not exist because it's not the same on the left and the right. So since they are not the same, it does not exist. So that's just a good thing to keep in the back of your mind, is to make sure it's something that actually can be done. Okay? because on the left side it doesn't work. So just keep that in mind. All right, another example. We're going to say let f of x be equal to the piecewise function 4x minus 3 if x is less than 2. And we're going to do the quantity x minus 3 squared if x is greater than or equal to 2. First thing I want to do is the limit as x approaches 2 from the left of f of x. So let's think about this. I'm approaching 2 from the left. So I've got to look at this, since this is split up into 2 halves, I've got to look at this and say, which one of these is on the left side? Well, since right here it says x is less than 2, that's my left-hand side right here. So for going from the left-hand side, I'm going to use 4x minus 3. So that's the limit as x approaches 2. Of 4x minus 3, because I'm going from the left-hand side, and so I want the one on the left. So as I have seen, I can just plug in 2 here. So that's just going to be 4 times 2 minus 3. 4 times 2 is 8, so that's 8 minus 3, which is 5. So going from the left, it's equal to 5. But then part B asks for the right-hand side. So on the right-hand side, that's all things greater than 2, so I'm going to use this one. So that's the limit as x approaches 2 of x minus 3 squared, because I'm going from the right-hand side. As I know, I can just plug it in, so that's just going to be 2 minus 3 squared. 2 minus 3 is negative 1, so negative 1 squared, which is 1. So from the left, it's equal to 5, and from the right, it's equal to 1. So when part C asks for the limit as x approaches 2 of f of x, I would say that does not exist because it's not the same on the 2 sides. So it does not work out. So on these ones, just be careful and look at which one I want to do. Since part A asks for the left side, I'm using the one on the left, right? Since part B asks for the right side, I'm using the one on the right. Another example like this. Let's let f of x be equal to the piecewise function. This one will have 3 terms. Negative x minus 2 if x is less than negative 1. 2 if x is equal to negative 1. And x cubed if x is greater than negative 1. So for part A, let's do the limit as x approaches negative 1 from the left. So again, from the left-hand side, I want everything smaller than that, right? So that's my top one. So for the left-hand side, I'm using this one. So that's the limit as x approaches negative 1 of negative x minus 2. So now I can just plug it in. So that's negative 1 minus 2. The minus signs cancel out, so that's 1 minus 2, which is negative 1. Again, for the left-hand side, I'm using where everything is smaller, so that's the top one. Now for the right-hand side, I would use everything greater than, so that's the bottom one. So that's the limit as x approaches negative 1 of x cubed. Again, I can just plug it in, so that's negative 1 cubed, which is negative 1. So when they ask for what the limit as x approaches negative 1 is, since they are the same, I can tell you that's equal to negative 1. Again, I can only say that because they are the same. Whereas on the last one, they weren't. And so I couldn't do that, right? So on these, just make sure you are trying to go from the right side that they want. All right, we only have 2 more examples we're going to do. 2 more examples. That's going to be the limit as x approaches 2 from the left of x minus 3 over x squared minus 2x. Approaching 2 from the left. Okay, so again, what I would normally try is see, okay, can I plug in 2? But I can't, because this would be 2 squared minus 2 times 2, which is 4 minus 4, so I can't, right? So I would try to rewrite this as best as I can. So that's the limit as x approaches 2 from the left. The numerator cannot be factored, so we're just going to leave that x minus 3. The denominator, I can factor out an x, so that's going to be x times x minus 2. But unfortunately, that doesn't really help us out here, right? Because there's nothing I can cancel out. So I'm going to have to try this another way, okay? So what I'm going to do is I'm actually going to split this into 2. So since I'm trying to plug in a 2, the factor that will screw that up is if I plugged in a 2 into x minus 2, right? That's where I kind of can't plug in 2. So what I'm going to do is I'm going to separate it and put that factor by itself. So I'm going to have x minus 3 over x, and then let's leave 1 over x minus 2 on its own, since that's the one that's causing me problems. Okay? So I'm going to start right here. This one I can actually just plug into, and that's fine. So let's do that. If I plugged in a 2 into that, that would be 2 minus 3, which is negative 1 over 2. So negative 1/2. I get negative 1/2 right there. That's good. Times, let's see what happens right here. Okay. So I'm plugging in numbers getting really close to 2 on the left-hand side right there. So that means I'm doing like 1.9, 1.99, 1.999, and on and on and on. As I'm plugging in numbers getting closer and closer to 2, I can see this is getting closer and closer and closer to 1 over 0, right? Because that's what will happen here. So if I'm dividing 1 by a number that's really, really, really small, we actually saw in section 2.2, this means it's getting really, really, really big, right? 1 over a value very small is very big. So let's look at that, right? So like 1 over something very small is like 0.000000001 is really big, right? So that's what happens here. But since I'm saying it's to the left-hand side, that's like 1.9, 1.99, and blah, blah, blah. So this is actually always going to be negative. So the limit here is going to be negative infinity. Again, because it's something really big, but with the minus sign because it's 1.9, 1.99, all of that stuff. And so when I subtract 2, it's going to be a negative. Okay. So what I end up with is negative 1/2 times negative infinity. The negatives cancel out and make it positive. 1/2 times stuff that's really big is still very big, right? So this is going to be positive infinity right here. So just to recap what I did there, we needed to split up the factor that's making it to where I can't again a 2, right, which would be this one. So I split it up, x minus 3 over an x, and then 1 over x minus 2. I could do that one, so just plug in 2 there. This one I have to really think about, right? The bottom is getting closer to 0, which means the whole thing is getting really big. But since I'm on the left side, it's negative. Negative twice makes it positive, and it's getting very big, and so it's going to be positive infinity. Let's do another one like that to make sure we're good with it. one more. This is our last one. Let's do the limit as x approaches 1 of x plus 2 over x plus 1 squared. Okay, so again, I would try to plug in a 1. Oh, I can actually plug in 1. Oh, this is supposed to be x minus 1. I was like, that is too easy. There's no way. X minus 1 squared. So sorry about that. Okay, again, if I were to try to plug in a 1, it doesn't work, right? And so just like I did, I want to try to split this up. The factor messing me up here is x minus 1 squared because I can't plug it in, right? So we're going to separate this into the limit as x approaches 1 of. X plus 2 is good, so I can just leave that as x plus 2. But I can't plug it into x minus 1 squared, so leave that as 1 over x minus 1 squared. So this one I can do, right? I could just put in the 1 right there. That's going to be 1 plus 2, which is 3. Easy enough. That one, that's not that bad, right? But this one over here, again, we are going to have to think it out, okay? If I plugged in a number really close to the 1, I would get something very close to 0 inside of here. 0 squared is still 0, so that's going to be 1 over 0, which, as we said, means I am dividing by stuff that's very small, right? 1 over a thing that's very small, as we have seen, makes it really big. So I know it's going to be infinity, but I want to know what the sign is, okay? Since this is squared, the bottom will always be positive, right? The bottom will always be positive. So because of that, it's positive. 3 times a number that's very big is going to be very big. So just like that. So those last two require a lot of thought, more so than being able to like plug in stuff, right? All right, so that was a lot of stuff we did, but that is the end of what we are going to do in section 2.3. Remember, if any part of that did not make sense, please let me know. I will be happy to help out. Okay. Thank you, guys.